All right. Oh, how about now? Can you hear me in the back? Hear me in the back? All right.
Your thing is on the screen.
So what?
Your thing is on the screen.
My thing is.
Yeah, it's just on the top left.
Oh, I see. This is not supposed to be what you want to see?
I mean, if you're to the top left corner, maybe.
Yeah. What if that's where all the good content is?
Like file, edit, view.
Exactly. Who needs those things? Okay, that seems fine, right? See, remember what I said about OBS? Somebody should fix it. This is garbage. Don't apologize for OBS.
No.
Okay. We good? We good? We can see in here. All good. All right, cool. Okay, we are on the other side of Halloween, so happy November. It's definitely way too early for Christmas stuff. I can't believe that's already starting. But I do have, I guess, to celebrate the demise of Halloween, I do have candy. So if you answer questions, no, you don't get it for free. What's wrong with you? You only get it for free when you're children trick or treating. You're adults. You answer questions, and I'll try to throw candy at you, and then you can get some candy. Yeah? I heard a trick where some professors said that they would, now you evaluate professors and do course reviews like when you're home. But back in my day, you had to do it like on paper in class, like a professor would pass it out. And some people I knew would bring candy whenever those were passed out and just happen to give candy to the whole class on those days. I don't know if it works. Yeah.
If you throw candy out, is that considered work with hazard or no?
Depends if you catch it or not.
So that's the argument, but it doesn't.
Yeah, life's risky. Yeah. Can you fabricate questions? No. No. I ask questions and you answer. It's not the other way around.
But if I ask you a question, you ask me back.
Maybe. We'll see. I'm the arbiter of the candy, so whenever I feel like giving out candy, you'll get
candy.
candy.
Ask a question, and then you answer. So I throw you a candy.
If you have candy.
I do, but I don't want it.
You don't want to do that? Then don't do that. Also, don't randomly throw candy at me if I'm not ready. Okay. It's supposed to be fun. Cool. All right. So we've been talking about cryptography. And so somebody refresh us. What is the key difference between asymmetric cryptography and symmetric cryptography? Yeah.
Symmetric cryptography uses the same key for both encryption and encryption, but asymmetric doesn't.
Okay. Asymmetric does what? What's the key difference? No. Follow. That's a follow-up question to you.
Isn't it like break up the message and then it encrypts it and then it uses that encryption as the key?
So yeah, I think the key is it's different to just say it's not that there is no shared key, right? There are keys that have to be shared, but everyone has essentially two keys, a public key and a private key. All right, paying attention. That's pretty good. This is gonna be a great class. Great. Okay. Yeah. So the idea being thinking of so symmetric for sure. There's one key that's shared, but wait, why is it showing this part of my screen?
Because that's candy.
What?
Oh, I thought you were talking about camera.
Oh, yeah. Everything is messed up. Okay, you talk to me. There you go. Okay. All right. I guess these slides are fine. If you're on Twitch and if this looks weird, this presenter viewed, say something, and I will fix it.
I'm looking at it. It looks like you can still see the slides. It's just a little strong.
Yeah, I'm looking at it here. Okay. We'll see how that works. Okay. So, and we looked at asymmetric crypto systems. We saw that we can get all kinds of cool stuff. We can get encryption. So if we have Alice and Bob, they both have public keys. They both have secret keys. How can Bob send a message to Alice so that only Alice can read it? Yeah.
The pronounceable thing I can't say encryption. The dial.
No, we haven't got there yet. That's next content. In the back. Yeah, so Bob can use Alice's public key, encrypt the message to get ciphertext. That ciphertext can only be decrypted with Alice's secret key. Exactly. Okay, do you think I can throw this far? Are you willing to try? Okay, that's good. I feel like it. Oh, but then not even halfway. Okay, I gotta try again. That was pretty good, right? Thank you. I can't do that again. I will, if I can already feel that it's not good for my arm. You may have to come closer to collect said candy. Somebody make sure you get that one on like row 4 or 5. Yeah.
Have we talked about like what the connection between the public and secret key is?
We have not. We're going to get there right next. Yeah. So now we're talking about this as a high level because this is really the key thing of understanding how do I use these systems? How do I use the different keys? So we just talked about encrypting. What about non-repudiation? So if Bob wants to transmit a message and that everyone cryptographically knows that that message comes from Bob, what can Bob do? Yeah. You already have a candy.
Don't give me a candy.
Okay. Answer that.
He would just encrypt it with his own secret key.
Okay, he encrypts it with his own secret key, and why does that help? How does then everyone else? So if I get that message from Bob, how do I then verify that it comes from Bob?
Because nobody should have his secret key, so if you're able to decrypt it with the public key.
Exactly. I use Bob's public key to decrypt that message, which I know everyone can do, which why it doesn't guarantee encryption and it doesn't guarantee confidentiality, but I'm able to say that this actually comes from Bob. Okay, great. I was just kidding, unfortunately. So how do we do that? There you go. Cool. Yes, non-repudiation. Excellent. And we just also talked about, this is the more complicated one. I want to send a message. So we'll stick with Alice and Bob. Bob wants to send a message to Alice such that only Alice can read the message and that Alice can verify comes from Bob. So let's pointer, pen. So I have my message M. So Bob wants to send a message to Alice. That message M that is both confidential and that Alice will know comes from Bob.
I'm not sure what you are, but like Bob first encrypts it with Alice's public.
So the public key of Alice encrypts the message. So which part does this guarantee?
It guarantees that Alice is the only one who can.
So that Alice is the only one that decrypts it, but anyone can do this, right?
Yeah.
So like Mallory or Eve, the evil person, can make another message prime, and encrypt that with Alice's public key.
And then probably like one thing if
Bless you.
Bob can also encrypt it with his secret person.
So the secret key of Bob,
Yeah.
like this. Okay, so we get that. And then, so one thing, make sure it's correct. So Bob can, the outer layer, apply, so that would give you C. And so if you then take that, apply first the public key of Bob to then get the middle, and then the,
And then apply, then Alice applies her secret.
but the message is from Bob to Alice. Bob doesn't have access to Alice's secret key.
Oh. Wait, doesn't Bob just send it like after encrypting it twice, once with Alice's public key, and then on top of it, it also encrypts it with his secret key, and then he sends it.
Yeah, okay, okay. So this is from Bob to Alice. Wait, maybe I got confused. Okay, so Alice uses Bob's public key to encrypt the outer layer. Then Alice uses her secret key to encrypt the message.
Yeah.
So great. Okay, so we get the message back. Now if Eve, our malicious Eve, gets this message, right? Gets C. What can Eve do?
Eve can use Bob's
Can use Bob's public key, and to get, so she can apply Bob's public key to get the inside of the public key of A of M.
Yeah.
And then she could substitute in her own M prime. And then, so the problem with this scheme is it's not like the outer layer is not being protected, right? We can actually go in there and we can't decrypt this, so we can't know exactly what's being sent, but we can modify it and mess with it, right? And that's the key problem with this approach. What we really want to be doing is, so on the outermost layer, so the very first thing we want to do is encrypt it with the secret key of Bob. So Bob uses his secret key for the message. So this gets non-repudiation so that Alice will know that came from Bob. And then on that, we want to use the public key of Alice. And at this point, there's no possible way that anybody can look inside this message at all. So there's no way of peeling off that outer layer. So that's the way to get there. Yeah, it's complicated, but important. Okay, so now we can understand. Oh, here. You actually gave like a couple options. Can you rapid fire catch? All right. So now that we've talked about these schemes, what they are, now we'll get into how they're implemented. And there's several different styles of these public-private key crypto systems. Again, I'm not like a hardcore math person, so I will give you the shape and flavor of why this stuff works. But again, you can dig into the math to figure this stuff out more. What's crazy interesting to me is that this stuff, the concepts of, so we already kind of know what has to exist, right? We talked about it. So we have these public key and a secret key, and it should be very, there has to be some relation. Otherwise, this stuff is probably not going to work. But it should be the case that it's difficult if you have the public key to derive the secret key, right? If it was trivial, then you don't have anything, and you need to keep that public key secret too. And now you're at a symmetric crypto system. So the seeds of this idea go all the way back to 1874. So this says, the same difficulty arises in many scientific processes. Given any two numbers, we may, by a simple and infallible process, obtain their product. Do you know how to do this simple and infallible process to attain a product? What's that? Multiplication. Oh, sorry. I was trying to get it around the camera. Multiplication to obtain their product, but it is quite another matter when a large number is given to determine its factors. Can the reader say what two numbers multiplied together will produce the number, is this billion? 8,616,460,799? Do you know this off the top of your head? Sorry, I'm trying to think of more of who asked the question, but it's good. Yeah, so one way we could do this. So here, take a thing. Oh, that was so close. All right. Guess I'll never be an NFL quarterback. Okay. So one way we could figure this out is try dividing this number by, well, we don't need to do 1. Will 2 work? No, we can already see because it's an odd number. Yeah.
We can cut out all numbers since it's or all even numbers since it's not numbers.
Yeah, we can start doing things like that. We can maybe do it cleverly, but the stupid way would just be trying all those numbers. Here, you think you can catch? Do you want to try to catch?
No.
Okay. Do you want to come up here?
Yeah.
Nah, there we go. This will be the candy table. Okay, but one simple way we could do this, we know two numbers multiplied together resulted in this number, but we don't know what those are, so we can just try all numbers smaller than that until we get two numbers that multiply together. Yeah.
Well, I was thinking about prime factorization. I'm not sure about this number.
Exactly. So maybe there are cleverer algorithms. Okay, this is the one where it has involved. Okay. Oh, so close. But maybe this will boost the Twitch stream numbers if I just throw the candy at people. Apparently not. No, that would be. I don't want you in the video, just me. But that would be a good if I was producing this. Anyways, so there are maybe cleverer ways we can try to do this, but fundamentally we have to try a bunch, and we can all agree, and we'll see that's actually difficult, right? The multiplication step is trivial. It took this person in 1874, I wouldn't say 2 seconds, but doing longhand, doing this out, you could do this, right? You learned how to do this as children in school. And this is what the author continues to go on. I think it unlikely that anyone but myself will ever know, for they are too large prime numbers and can only be rediscovered by trying in succession a long series of prime divisors until the right one is fallen upon. I like that one. Fallen upon. The work would probably occupy a good computer for many weeks. Wait a minute. What are they? Did I just lie to you that this was 1874 and he's talking about computers? What does he mean?
There used to be people whose entire job was just to compute the numbers.
Yeah, computing numbers by hands using books and tables and all kinds of crazy stuff. Yeah, so that's what he's talking about here. But just a quick fact check. He's not a time traveler. For many weeks, but it did not occupy me many minutes to multiply the two factors together. Similarly, there is no direct process for discovering whether a number is a prime or not. It is only by exhaustively trying all inferior numbers, which could be divisors, we could show there is none, blah, 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 blah. And the labor of the process would be intolerable were it not performed systematically once for all in the process known as the sieve of Aristophanes. Thank you. The result being registered in tables of prime numbers. So this is crazy. This is a hint, even back in 1874, that there is a mathematical process that is very easy to do one way, multiplication, but very difficult to undo when those numbers are prime. This notion and this seed of people that started exploring this kind of finally realized like they could connect these ideas together. That's been in math and in number theory for a long time. In 1976, Diffie and Hellman, which we'll talk about, published a way of exchanging keys in The Secret. This is actually like mind-blowing that this works. It's so cool. In 1977, Ron Rivest, Adi Shamir, and Leonard Adelman created RSA, made from their initials, which is the General Public Key Crypto System, which is super cool. And some interesting things when you get into like who developed what. Remember we talked about the NSA had linear cryptanalysts of DES before that was ever known by the public. Similarly, the concept of public key crypto was invented by a British cryptographer in 1970. So I think that's pretty interesting. And then in 1973, one of that person's colleagues actually also invented RSA. So there's kind of an interesting sub-question here of like who gets credit for this invention if we only know about the NSA or not the NSA, but the classified advances decades after they actually happened. So the folks on the top, the public people, are the ones who actually get the credit for inventing these, but it's interesting to see that these ideas sprung up. And what I also find interesting is that time gap, right, between the discovering these things in the classified space versus the public space. It's an open problem, especially for somebody like me who doesn't have classified clearance or anything. You can think about what's the gap nowadays. Is it a 6-year gap like here? Or is it a shorter gap, longer gap? I don't know. Yeah. Do you have a guess?
Probably guess it's still around 6 to 7 years.
I don't know, but I bet there are people that know. Right? Because it's kind of interesting. You can have the people in the classified space, they have all the knowledge that's in the public space plus their own classified knowledge, right? So they can probably estimate how far in advance they are. Anyways, so let's get into Diffie-Hellman's idea of public key cryptography by talking about paint. So Is this like a true analogy? I don't know. I don't know if paint mixing actually works exactly like this. Is that true?
Sure.
I don't know. Do colors work when you mix them like this? Like, is this a paint?
This follows color problem.
This is a valid color theory demonstration. I don't know if this is true, but I think it might be too, just because it's on Wikipedia. But I feel like that's a bad argument in my
It's either
head.
additive or subtractive. I don't know.
Exactly. Okay. Cool.
So I guess where it stops on the spectrum is
Okay. So Alice and Bob randomly decide on a color that they share in the clear with each other. So on the left, sorry, it'll be more clear as we go on. On the left is everything Alice knows. On the far left, on the middle is going to be the information that Alice and Bob exchange. On the far left is going to be all of Alice's secret knowledge that only Alice knows. On the far right will be Bob's secret knowledge that only Bob knows. And on the bottom is everything that Mallory knows, because Mallory can watch everything that happens in the open, but she can't know about anything that happens secretly that only Alice or Bob does. Make sense? And don't worry, you can still follow this even if you're like colorblind and stuff. I think these colors are colorblind safe. So randomly decide on an initial color. Let's say it's yellow. They exchange that with each other. They then both randomly decide on a different secret color. In Alice's case, it's like a orange. If somebody like had one of those giant box of Crayola crayons as a child and remembers what exactly those colors are, I don't know if this is like a burnt orange or something, or this is a cyan for Bob. I'm sorry, I'll probably just use orange and blue, but you feel free to suggest better ones. But Alice generates an orange-like color. Bob generates a yellow-like color. Teal? Sorry, did I say yellow?
Yes.
Oh, sorry. I was looking at the yellow one when I was talking. Okay, yes. The blue teal-like color. And then they combine those. So by using the public information, the yellow, Alice combines the yellow with the... See, the problem is it's a different color on there than I'm seeing on my thing. So, whatever. The yellow with the orange to get slightly lighter orange. Bob adds the yellow plus the teal to get, I want to say periwinkle. Is that a good guess? Like a light, almost like a lilac blue. It looks periwinkle on my screen. Thank you very much. Dark sky blue? Okay. Anyways, looks like, see, they say baby blue on Twitch, so I think I'm correct. Okay. A lighter-ish bluish color that is definitely different from that teal. And then they share those colors with each other. So what does Mallory know at this point?
Well, she knows that Alice has this orange color and Bob has this bluish color.
Yes, Alice has the bluish color. Alice has the orangish color. Bob has the bluish color. And they each know each other's one that they just shared. So now the state of the information is that Alice knows about this bluish color of Bob, and Bob now knows of this orange color of Alice, and Mallory knows all three colors. What's the piece of information that Mallory does not know? Louder?
Ours was blended like from
Yeah, doesn't know these colors, right? The dark orange for Alice and the cyan teal for Bob. Yeah.
if they have the public key and they have
No, these aren't keys. We're talking about paint.
the public paint.
Yeah.
And they have
Which
the
color?
paint, yellow and
Yes.
let's say orange, for example.
Yes.
Can't you just XOR or like figure out the mixture?
So,
Force essentially.
right. So this, you could maybe, the problem is how do you subtract paint colors? I think it's like fundamentally a difficult thing to do. We'll assume for these things. I don't know anything about paints or colors.
Get the next course more colors.
No. It's physical paint. It's not anything with colors.
Isn't that like why you talk about prime number colors? Because it's like easy to mix it one way, but you can't really
Exactly. It's very easy to mix paint together. It's hard to separate them into what exactly I missed because it's mixed. Because it should be, I think there should be multiple pairs of paints that could get you to similar things. And so just buy that argument and then everything else follows. Yeah. We'll show how you do this with actual math. That's the cool thing. But for now, we're just talking paints. So now, by combining, Alice and Bob can both, this is the magic part, Alice and Bob can both combine their randomly generated one with, so the orange, the dark orange, plus the light orange, plus the, I'll say baby blue, and get this super muddy brown color. Bob can also combine the cyan, the light blue, and the light orange to get this dark brown color. And it's exactly the same color that they're both able to derive. So we've reached a state now where Mallory can't combine any of these colors together in order to infer and get what each of them has separately derived. So you reach this crazy state where Alice and Bob now know something that only they know, that Mallory cannot know, when they've only exchanged information in the clear. Kind of crazy, huh? And this is the whole thing that this entire scheme relies on. And now, for instance, if this brown color was a AES key, now they've collaboratively derived exactly the same AES key that they can now use to encrypt some communication and start a secure message. But Mallory can't derive that same key with the information that she has. Or rather than say can't, I think the proper thing is we create the system such that it's computationally infeasible for Mallory to do that. Questions? It's kind of like insane that this works. And this is why, so the other important thing, this is why this is like one of the first public key crypto systems, because it's not a true public key crypto where you have a public and a private key, but you can see that they're able to derive a shared secret that only two parties know by only transmitting public messages. So this, you can see, can be used to generate that key that can be used for symmetric crypto. We'll see that RSA is a general purpose public-private key crypto system. Okay. Now, to get some intuition about why this works, we now need to think about, we're going to look at some math of what's actually happening behind the scenes. Okay. So a little bit of math refresher. Commutative property on some type of operation, any type of operation. It seems like, I don't know. When was the last time you saw this on like in a class? $230? Wait, math 230? Yeah, like a math class? Is it like discrete math or whatever is like math for computer scientists or something? Yeah, right? Or you probably actually learned this all the way, maybe, I think I remember learning this like back in algebra, right? Where you learn about the property and you're probably at the time, you're like, why the heck am I learning this stuff? It'll never come up again. Spoiler alert. So, okay. So we have several operations that are commutative and some that are non-commutative, right? So subtraction, you can't just swap the order that you apply them in matters. Division, matrix multiplication, but integer addition, integer multiplication, and paint mixing are all commutative operations that we have stated in our paint mixing world. Okay. Now we need to talk about another operator that I'm sure you love, and now I'm going to fix this slide because we just talked about it on the way here. The other ones, it's correct because they're mod 13. Okay. So the mod operator. Somebody remind me what that does. Who hasn't had candy? Yeah, you.
Basically divides a number by whatever number and gives you the remainder.
Divides a number by another number and gives you the remainder. Yeah, you think you can catch a starburst?
Yeah.
Oh, that was perfect.
Right for the heart. Nice.
Okay, yes. And in principle, what does this do? So the result will be like, how does this affect the range of the result? Yes.
The results can only be, in this case, 0 through all of integers, 0 through 11.
Yeah, so the results only be 0 through 11, right? Nice catch. Okay, cool. When have you used the mod operator when programming? Is it useful?
Yeah, it's pretty nice.
Wait, somebody raise their hand and tell me when. You were nodding. Yeah.
I had to do something that was like recently finding factor surface multiple something.
Mm-hmm.
So you have to check them if it was zero.
Okay, cool. So factors. What about any other cases? Yeah.
You can use mod
Use it to find out if a number is even or odd. So you do mod 2, and that gives you a 1 or a 0. Yeah, awesome. You can also use it to restrict ranges of things, right? So if you have do a circular buffer, like that's a size of 200 or something, you can do mod 200. That way you know you'll always stay within that size. Cool. And we can think about it like a clock. Have you ever thought about a clock as like a mod 12? It's kind of what it is, right? When somebody tells you like, meet me at 1300 hours, what time do they mean on a clock like this?
13 plus 12.
Yeah, 1, right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All of these. Now, we'll look at a different kind of clock. So this is the clock that we're normally used to thinking about in terms of mod. Now, it turns out, and why does this happen, Adam? I don't know. This is all math stuff. So if you have two numbers that are I believe is a requirement that they're co-prime or they're both prime? 7 and 13? Doesn't have to be co-prime. They just need to be two random, and the smaller one is this one, right?
It needs to be like a generator, which has some.
See, exactly. Crazy math stuff. So, so we can define. I can probably pop forward and check here, but that's okay. Anyways, that will tell us. We'll get there eventually. Okay. So, sorry, I'm jumping around. Okay, what this does. So now we have n. So 7 to the n mod 13. Everyone know what exponentiation is? Right? 7 to 0 is all together now? 1. 7 to the 1 is 7. 7 to the 2 is 49. After that, I don't care. I don't know. It's too much, too big. But you could take each of those results and mod 13. So we can do that, right? So we can do 7 to the 0 is 1. Mod 13 is going to be what? 1. And 2, so that was 0. So 7 to the 1 is 7. Mod 13 is what? 7. 49 mod 13 turns out to be 10 if you do the math. You don't have to do the math. That's fine. And so you can actually continually do this from 0, 1, 2, 3, 4, 5, 6, 7, all of the numbers up there. And what you'll get is now you get the same mod type operation where the results will always be from 0 to 13. Where's 0 on here?
There's no 0. You can't have 0.
Oh, you can't have 0. Interesting. Fascinating. Oh, does that make sense? Oh, because it'll never be. Interesting. Okay.
There's only 12 values.
Got it. Wait, why was there? Sorry, you guys can't see the stream, but balloons just shot up on the stream. It was very weird on my camera. Okay. I think it's the AI going crazy. Okay, so the results in this case will then be 1 through 1 minus the thing. So we have 1, 2, 3. But, and this is the very, very, very important thing, unlike this modulo operator where the result was exactly 1 more, right? So 0, 1, 2, 3. Now you can think of this as this essentially randomizes what the next number is. We have to like do these calculations. So 1, 7, 10, 5, 9, 11. And I believe we can then use this to do math here on this beautiful, our beautiful friend, Mr. Clock, 7 to the n mod 13. Yeah. So, oh, good. We have it all here. So 0 would be here. 1 is 7. 5 is 11. -2 is 4. And if we do 1 plus 1, oh, great. Is that, okay. I don't recall why this is important. Why is this important?
It just shows you can do addition and multiplication.
Yeah, okay, great. So yeah, we can do it just like before. We can do addition, multiplication, all on this table, moving around at different points. And so we can actually, it turns out, use this property in order to actually implement this Diffie-Hellman key exchange. Cool. So steps of the operation are Alice and Bob agree on some P and G, where P is prime. So P is going to be the mod. So the requirement is this mod has to be prime. And G is a primitive root modulo P. What the? I don't remember
It
that.
just means it literally has that property that you get all the values in the group.
Oh, perfect. Okay, so it looks something like this, that you get all 12 in that circle. See? Cool. Then, so this is that information they exchange. In our example, the yellow paint are these two numbers. Then Alice chooses a secret integer A to send Bob G to the A mod P. So Alice computes that operation, so looks at her clock and says, okay, where is this number? Great, send that to Bob. Bob chooses a random secret integer B, sends G to the B mod P to Bob. So similar thing, calculates where on Bob's clock and sends that result. So these are all sent in the clear. So Mallory would know P, G, capital A, and capital B. Alice then computes B to the A mod P. So takes B, raises it to the A mod P. That gets S, and Bob is able to compute the same secret, taking Alice's secret, raised to the B mod P. And why this works, so this is actually like, I guess, incredibly simple math of why this works. So what we're doing here, right, is taking B, let me draw. Pointer. So, oh wait, this is G-A-B. Yeah, so this is A. So A, capital A to the B. Oh God. Mod P. Right? So just taking this, which is this, is S. So expanding out A gives you G to the A mod P to the B mod P. B can go into and pass in here. So this is the same thing as G to the AB mod P. And because we can, multiplication is commutative, we can swap those. So we can do G to the A times B mod P. And with that, we can then take A out. And this is G to the B mod P raised to the A mod P. And what is this inside here? What B? Yeah, big B, right? Big B to the A mod P, which is what? What's big B to the A mod P? Yeah. Yeah, it is. But what in here, what is it?
Also A to the
S. Somebody said it. It's S. Yeah. So on both sides here, you get S, right? You get S is B to the A mod P. And then we do these transformations. And at the very end, we get B to the A mod P, which is the same as S. And so this shows that they each derive this secret S. And I believe this all derives on the fact that it's very difficult if I said, okay, I have 7 to the 0, 1, 2 mod 13. If I am multiplying this number times this number, that would give me 1, 2, 3, 4, 5, 6. 2 times 6 would be 12. So that would go here, I think. 2. This one, the very top one. We want me to count all of this? Oh, yeah, it's a 6 to 12. Yeah, that makes sense. So it goes up here. The result would be 1. But if you knew just the result was 1, it's difficult to know which of those I multiplied together to get back because it's a giant circle. You could try each of them. But if this circle was incredibly large with a lot of numbers in here, it would take you a very, very, very long time to try all of them, which is why this is an example where we show you because we can do the math very easily. But real systems have to use large, very large numbers. So we can now apply this to our paint mixing analogy. And so in this case, Alice and Bob both agree in the clear to use 23 and 5. This would be, so 23 would be P and 5 would be Q. So P, this is the mod operator. And so it's 5 to the n mod 23 is going to be the scheme that we're using. So they will randomly choose an integer, so 7 and 10. They will perform the addition. So here we have 5 to the 7 mod 23 is equal to 17. Bob calculates 5 to the 10 mod 23 is equal to 9. So we can see the linkage between the colors here, right? So this is how they're able to derive and mix the paint, if you will. Then they exchange those numbers with each other. So they send each other 17 and 9, so they both know that. Now they combine these. So they do 9 to the 7 mod 23 is equal to 4. And Bob does 17 to the 10 mod 23 is equal to 4. And that's how they're both able to get the brown numbers. But Mallory, with using the information that she has, cannot calculate what that secret value is without trying all the values. Questions? This is nuts, right? And this is like one of the basis of what all of our secure communications is based off of, which is also nuts. Like, in its simple quote, I guess simple is a relative term, but it's simple-ish mathematical properties like these that we're able to identify and prove and then actually use.
I don't think it's actually proven.
You don't think it's proven?
It's really long being parts of proven. It's just how do you do it?
Interesting. Yeah.
SSH keys also generated from this.
Ah, yes. No, the answer is they're not. This, I think Diffie-Hellman is still used, if I remember correctly. It's still used for forward secrecy. The idea being, so we'll actually look at SSH keys. SSH keys currently, you can use RSA, which what we'll talk about, which uses primes and prime factorizations. The problem with those is actually, I guess, is quantum computing. So they have theorized quantum algorithms for factoring prime numbers, and that you have to significantly increase the size of your RSA keys to make those theoretically safe. And so we've actually started moving to elliptic curves, which have similar properties to this and with prime factorization. But as far as we know, the elliptic curve constructions can't be defeated easily by a quantum computer, as far as we know. Yes, and that's why, exactly, because as we'll see, right, or as even our of like how we talked about public-private key, right? So our adversary Eve can store all the messages that she sees, and then knows public keys, so she can try breaking all the public keys to get the secret keys. And if she has a very clever way of doing that we don't have access to, then she can now go back historically and read all those messages. So Diffie-Hellman, I believe, is used to do some forward secrecy to say that like even if the SSH keys are broken or the RSA keys are broken, we still have some guarantees there. Sorry, people had hands raised while I was talking about quantum stuff. Yeah.
So about the, what do you say, elliptic curves?
Elliptic curves. I don't know anything about them except for the things I've literally just told you. So, but you feel free to ask.
I was going to ask, how do you not know that it cannot be like encrypted easily with traditional computers too?
Yeah, great question. I don't know. Smart people think about these things.
All right, cool.
Yeah. Cool. So now we can look at RSA. So this is the Diffie-Hellman construction. Part of what you're doing in your assignment is actually building this and doing this, and you can see it's actually not crazy math. I mean, this is just you're using very simple primitives. So with RSA, now we'll see we have a more general crypto system, a public key crypto system with a public key and a private key, and you can generate RSA keys yourself. Does anybody know off the top of their head whether their RSA key or their SSH key is RSA? So it'll have I think if it ends in like ID underscore ED whatever or EC is elliptic curve, and if it's ID underscore RSA something, then it's an RSA key. Yeah, so you're using this stuff all the time to access the servers. Cool. So RSA key generation. So first, and this is generating the keys. So this is now answering the question. So Diffie-Hellman, right? The whole point of that, like you have to have an exchange, right? You have to have another party that you're working with to derive some secret, right? But that's not a general purpose crypto system. So for RSA, what our goal is to actually be able to generate a public key and a secret key that are linked, but it's difficult to generate the private key from the public key. So to do that, first you have to choose two distinct prime numbers, P and Q. The other cool thing as you get into crypto, everything that I'm saying like is a thing that must be true, right? These are two distinct prime numbers. You'll look at ways that you can break them if these things like don't hold. So you can show that like if they're the same prime number, I'm sure there's like massive problems to that. There's also massive problems if any of these stages. So very first thing we do, just like our friend back in 1870 something. I really wish I'd memorized that off the top of my head. That would have been so cool. 1874. I was super close though. That was like two years off. We can compute this, right? So we can multiply numbers. Can computers multiply numbers? Yeah, computers real good at multiplying numbers, even large numbers, even numbers with 1,000 digits. They can still do it, right? It may be slower than just multiplying two 32-bit numbers, which you did in the assembly levels, but you can still do it. So the whole idea of this scheme is that if you give n to somebody, it is very difficult to figure out the factor into P and Q, right? Just like our friend back in 1974 said, aha, it took me 5 minutes or whatever. Actually, did he say exactly how long it took? Yeah, it did not occupy me many minutes to multiply the two factors together, but he thinks in his time it would have taken people weeks to try to figure out those numbers. So what we can do and our computers can do very quickly, it should be the case that it is very difficult for people to do that. So, okay. Cool. Okay. Okay, there are also some other ones, but it's pretty easy. Yeah, this is just saying that we can easily calculate a to the e mod n. And we know that P and Q are prime. So we can easily satisfy this. It's just saying that calculate that is easy. But if we have C, E, and N, calculating A going backwards from this is hard. That is the other requirement. Okay, so we calculate another number, M. So we have P minus 1 times Q minus 1. We choose an E between 1 and M. Compute E to the negative 1 mod M. and that gives us D. We can do this easily because E times D is equal to 1 mod M. We finally get our public key, which is N. So N we can't derive P and Q from, and D. And our secret key is going to be N comma E. So we keep E to ourselves. D is derived from E here. So the idea being, given N, because everyone knows N, it's hard to get back to P and Q. And given D, it is difficult to go back and derive E. Cool? Properties. Now, how do we encrypt things? So Alice wants to send a message M to Bob. Alice, now we can actually dig in, and rather than using our public keys just as these kind of blobs, and say like, oh, we just performed some stuff, we can actually look at what that stuff is. So Bob takes the private key, the public key of Bob, which is N of Bob and D of Bob. And we need to somehow then turn the message into an integer. This is like a key problem. We're going to be using exponentiation and operating on that. So, and this number M must be between 0 and NB. So there is a limit of, I think, exactly what you can do here. But again, oftentimes we're not going to try to encrypt the whole message M. We would encrypt some AES key or something with public key crypto, and then also send the message encrypted with a symmetric encryption. All right, Alice does M to the D mod N and gets C. So Alice has the message M. Alice uses N in there, calculates M to the D, so D of E mod N, and gets C. So now we have our ciphertext, C. Bob gets C to the E mod N using his E that he has secret and the N that everyone knows, and he's able to derive the message. So Eve has C, the public key of B, the public key of A, but because of this properties that this crypto system, and because it's difficult to factor these primes, Eve, it should be computationally infeasible for Eve to derive the message from the ciphertext. Cool. Okay. Okay. Well, anyways, this is what I just said. So I've been hinting at this all along. So we need to be able to send numbers, but like we don't want to send numbers. We want to send messages. We want to send arbitrary sized things. We want to send a 1 gigabyte file, right? That 1 gigabyte file is for sure going to be less than your public private key. Does anybody know the size of their public or private keys? Yeah, it's like, actually, we can look at mine, not my private key, of course. That would be very, 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 very bad. But we can look. So we can do ls-la/sh id rsa.pub. So my public key is 394 bytes. I do have an elliptic curve key, and that's 97 bytes. Cool. Can I show you this key? Yeah, because it's a public key. It's actually on my GitHub. You can actually see these keys. Will I cat it for you right here? No, because it's very trivial to make a mistake, because this is your private key and this is your public key. So it's super easy if you're demoing something to type in cat ~/.ssh/id_RSA tab enter, and then boom, now your private key is everywhere. So something to be mindful of, and is a terrible design decision of the SSH clients that they do this. Yeah.
Can't you just rotate your key?
Yeah, then I have to change it like everywhere. Yeah. I guess technically my private keys do have passwords, so there's another layer on top of that, but so you'd have to break my password first, but like I'd just rather you not have it in the first place. Okay. Cool. So all that math leads us to a place where we now have a crypto system that we can use to send messages to each other. But we actually hit a little bit of a problem, right? So I had said, well, we want to show and demonstrate non-repudiation, But to do so, we had to use our secret key on the entire message, right? But do I want to do that with a key that is then used to decrypt something? Like then the message itself is actually encrypted and it's not in plain text. And anyways, that turns into a lot of problems. So we have another giant problem that we've talked about of message integrity. So how can I guarantee and demonstrate to you that that a message has not been tampered with? Why might this be useful? In what cases? Yeah. Verify that the message is coming from the correct source. How would you do that? So you maybe get a message from the source that says, hey, this is what I expect the data to be, and then get the data that says this is the data, for instance. Yeah, what situations may that be useful? Yeah.
So if there's a man in the middle attack and someone intercepts that and gives you a wrong info, you can figure out from there that this is not the right message.
Yeah, so for instance, anybody installing software on their computer? Anybody run Linux or anything like that? Let's use a package manager. Yeah, guess what? You're actually downloading packages from, not always from, if you're using Ubuntu, you're not downloading them from Ubuntu. There's a whole network of people who will run servers and donate bandwidth and disk space to host these packages. But then if you think about it, that's insane. You have your computer, you type apt-get install Emacs, you connect to some random server, download that package and just run it on your computer. So now you've installed some random thing. So that seems like a terrible idea, right? Because how do you know? You want your computer to know and verify that the stuff that you're installing is exactly what the people intended. So this is another case where integrity may be important. Maybe it's not necessarily a man in the middle. Maybe you're like, if you think about this, like content distribution network, and they call it mirrors, right? You have servers that are mirroring content. How can you trust those other content and those other mirrors? So we really want, and the other question is for the cryptographic primitives we've looked at, one of their main properties is if I'm Mallory and I get a message and a bit is flipped in the message, in the ciphertext, you decrypt it, it's going to be completely gibberish. Now, how do I know the case between the sender's actually trying to send me random looking gibberish message versus it's actually gibberish? Right? Like, so I get some ciphertext. So if you think we have Eve in the middle, Alice is sending an encrypted message to Bob. It doesn't really matter which system. Mallory flips a bit and sends it on. Alice decrypts it and says, Bob must be trying to send me something weird. Or maybe it was a key that they're trying to exchange. And now that key is corrupted and completely different. And the question is, how do we know? So this is where we get into the concept and the notion of cryptographic hash functions. So these are super important to understand how they use. We'll be seeing, I think, hopefully, that how this can be used in authentication and identifying users, in password checking and verifying and authenticating a user. But fundamentally, what a hash function is it takes arbitrary input, so any size input, and produces a fixed size output. So let's say, I'm just going to try to remember one off the top of my head. I guess an easy one would be SHA-256, because that's 256 bytes on the output. So any data you give me, SHA-256 produces 256 bytes. So how could this be useful? So let's say I have this magic box that does this. Yeah, so hopefully if I send less data, right? So if my input data is 1,000 bytes and I get a specific bit string, 256 bytes output, if I send and remove the last byte, hopefully I get something completely arbitrary, like completely random, to detect that something changed, right? Also, if I flip one single bit, I would want different hash output. Would it be useful if I just take the first 256 bytes of the file, the data that you give me? So you give me arbitrary data. My hash function is I take the first 256 bytes and give that to you as the hash. Is that good or bad? Yeah, I can't throw that thing to you again, but you can answer. Yeah, it's very bad because it allows people to add stuff to the end. All the attacker would know, as long as I don't change the first 256 bytes, then I'm good and I can just modify things later. So some of the properties we want. So I guess think about it conceptually, right? And arbitrary size input, magic black box, fixed size output. Will there be the case that two inputs have the same hash output? Yes, no? Somebody want to make an argument for either?
Possibly if the hash output is smaller than the input.
So what is our input size? That's on the thing.
Arbitrary.
Arbitrary input and fixed size output. So will there be collisions?
Yeah.
Yeah, it must be. I think it's pigeonhole principle or something, but yeah, fundamentally, if you have arbitrarily sized input, so if you have 256 bytes, that is what, 2 to the 8 to the 256 or something? I don't know. That's a lot. Or it should be, is that right? 8 to the 256? How many bits is that?
256.
8 to the 256?
2 to 256.
2 to the 256? No, that's bits. Is it 256 bit?
Yeah, it's 256.
I kept saying byte. Okay. Anyways, 1.15 times 10 to the 77. So there's a lot of possible inputs, but I know if I keep applying that many, right, at a certain point, there will be some kind of collision. Other important property is we want it to be a one-way function in the sense that it is very easy to compute the hash and fast, but it's very difficult to go back. So if I give you a hash, it should be very difficult for you to tell me what input generated that. Or to another way, because there are collisions, to easily find another input that hashes there. This is actually can be used to people to timestamp making statements. Twitter was good for this. You could post on Twitter a hash, and then a month later, like if you have a prediction for who's going to win the World Series, you could tweet that now, take your message, hash it, post the hash, and then after the World Series, be like, I predicted this. Look, because I said this, and it hashed to this, and I said that 4 days ago. And assuming that it's very difficult to go back or to calculate a collision. Yeah, one key thing, I hope this is clear, it needs to be deterministic. When I say function here at the top, it's not just like a function you write, but a mathematical function. So the output only depends on the inputs. And the other property we really want is that a small change in the input just fundamentally changes the output. So you change the input a little, and the output changes dramatically. If we have something like this, we get really great properties. So as we talked about and saw, public key and asymmetric crypto systems are expensive. We didn't really talk about that, but the exponentiation on large numbers is actually pretty computationally intensive. And so Alice wants to make some statement M that everyone knows is from Alice. And so let's say M is very large. Now that hash reduces that output. And so now Alice takes a hash of that message, the output being 256 bits, and she encrypts that with her secret key. And this is what we call like the signature of M. So Alice now has a signature of M and the message M, right? Which kind of makes sense because what was the purpose? Like, why do we want to encrypt M with Alice's secret key? What's the point of that? Louder?
Verify that it's from Alice.
Yeah, just to verify that it's from Alice, right? So every single person should be able to get Alice's public key, decrypt the message to read it. Well, that seems like a waste. right? We want everyone to see the message. So we send the message in clear text, but we also add the signature of the message. So that way, anybody who wants to say, hey, did this come from Alice? They can take the message, hash it, and then take the signature, apply Alice's public key, check the computed hash, and make sure they match. And if our hash function is good, then we can be reasonably certain that it was difficult, like nobody else was able to create a message that hashed the same way. Yeah, so Bob can then check hash M, and hashing M is way, way, way faster than doing public private key crypto stuff on M. And this is exactly what, so we go back to the problem of your Ubuntu distributions installing packages. This is exactly what happens. Your Ubuntu system has keys of the maintainers, and it will, and also they publish a signed hash of all the packages. So that way when your machine downloads a package from a random mirror, it can do this it does do this exact process in order to stop somebody from manipulating with the packages. It's pretty crazy. This stuff like in action all the time. Bless you. Cool. So now Bob, yeah, at this point, we're now at the same situation as we had for non-repudiation. So now, Bob knows that the message M that Alice tried to send is what she intended, and Bob knows it hasn't been tampered with. There's no M prime. So what would happen if Eve sat in the middle between Alice and Bob and altered M to be M prime? What would happen? Yeah. Louder. Exactly. So the hash of M, so now the hash of M prime will be different than the hash of M, so the signatures won't match. Right. There's too many people in the way, so I'm going to go over here. They follow me. Sorry. You go. No, it's not a fight. All right, thank you. Okay, cool. So exactly. So altering the hash, altering the message, either way, right? So there's two things that Eve can do. Eve can either change the message or Eve can change the signature. Right? Can Eve change the message and put her own signature there? So Eve generates some new message M prime, calculates the hash of it, encrypts that hash with her secret key, and then gives that to Bob?
Her signature wouldn't match up with the signature of what Bob wants, right?
Bob only can validate the signature based on what he gets. So it would be...
So if he tries comparing the signature Eve sends to...
Yeah, so let's take it step by step. So we have... So Eve gives the secret key of E on the hash... I should have just used H of M prime and M prime. So Bob gets this, or Eve changes it. Eve thinks this comes from Alice. He gets it. What does he do? Yeah, tries to decrypt the signature. But what does he use to decrypt the signature? Exactly, Alice's public key. So he'll apply Alice's public key to this, and what will that decrypt to? Gibberish, garbage, and the hash will definitely not match, right? He'll hash message M prime, try to check it, it will definitely not match. Or it would fail the signature. Usually they have some sort of validation, so you can tell like, oh, if you try to decrypt something that was encrypted with a different public key. Anyways, yeah, the point is, by doing this, if Now, Bob can also verify that this was definitely a message sent by Eve if he has Eve's public key, right? But he cannot be tricked into thinking that this message came from Alice because he cannot pass the signature validation process for Alice. Cool. Questions on this?
Oh, so like use of word like signature is that does that mean like what exactly does that mean?
Yeah, so signature here we're just defining as hashing a message and then applying your secret key to it.
Okay, so that.
Yeah. Which is exactly what if you see something's been signed, like digitally signed, I guess depending on that's sometimes a marketing term, but like with public private key crypto actually involved, that's what a signature means. Yeah. Cool. Oh. Cool. And we can use a hash function all the time. Literally any website you log into is using hash functions. We use it for file or message integrity. So just like we said in terms of communication, password verification. So this actually is a different property. This is using the property that the website wants to store your password, but doesn't want to store your password, right? What the website actually wants is to check if you know the password that you gave earlier. But the website doesn't want to know your password because if they get compromised, then everybody knows their password. So what they do instead is you send them your password, they hash it, and they do some other things to it that we'll talk about later, and then store that in the database. And then later on, they can verify that it's you because you give the same input that hashes to the same thing. But when an attacker compromises the database, if it's done correctly, it should be very difficult. They can't go easily from the hash to the password. Unfortunately, as we'll see, what they can do is just guess passwords. So they hash password and look for all the passwords in the database or hashes in the database that map to password. And they will find people because people do this. Anyway, proof of work. So all of the crypto stuff, most of it runs on hashes. This is how Bitcoin actually operates under the hood. It's actually trying to find hashes that have a certain number of leading zeros, and the number of zeros corresponds with the difficulty of the finding the block. So each block that they find, this is what mining is literally all about, is just finding based on the current pool of transactions. You find some random value that you hash all together that gets a certain number of leading zeros, and the first person to do that within roughly, well, the first person to do that, which usually the network is made to do happen roughly in 10 minutes, they then tell everyone else and they give themselves 50 Bitcoins as part of that transaction. And that's how, or I think now it's 25. Is there still mining fees or mining bonuses? I think so, right? It's built in the protocol. I don't remember.
Because that's how you get like more Bitcoin into circulation. So like there's a limit.
Yeah, there's a limit on how much. Yeah, thank you. Okay, cool.
That's why they stop making new.
Also, anybody use Git? Yeah, have you seen random character-ish hexadecimal strings? Those are hashes. So Git is all done based on identifying data. So it is a commit is a hash, and it does that to represent a set of changes. So what Git's doing under the hood is you say, I want to change these files and commit it. It takes those changes, hashes that, so that way people can't rewrite history and stuff, and you can easily verify this stuff. Anyways, we will continue on to hash functions on Monday. Today was Wednesday, right? Okay, and if you didn't get any, come take some.
That's up stake more. I'll take this one. Question: do we?
Wait, just a second.
You just took two. Oh, thank you. Anyway, yeah.